All right, let's talk about a risk that might be hiding in plain sight, right inside your AI models. It's something that can turn your greatest asset into a major privacy liability. We're diving into membership inference attacks. And trust me, it's something every leader working with AI needs to have on their radar. This quote really just says it all, doesn't it? The very model that you've poured resources into, the one that's supposed to drive business value, can actually become a backdoor, leaking sensitive information about the very people's data helped build it. And this risk, it has a very, very real price tag. $10 million. That's not a hypothetical number. That was the actual remediation cost for just one financial firm after a breach from this exact type of attack. So we're not talking about a theoretical threat here. We're talking about a serious business cost. So let's really break this down. What is this hidden risk? And how on earth can an AI model, a piece of software, actually leak the data it was trained on? So what is a membership inference attack? Put simply, it's a way for an attacker to basically ask your model, hey, have you seen this person's data before? And here's the scary part. The model kind of answers. You see, models tend to be just a little bit more confident about data they were trained on. It's like they recognize it. This creates a sort of behavioral fingerprint that attackers can exploit to figure out who was in your training set. Now, why is this so dangerous? I mean, who cares if someone was in a training set? Well, because in many cases, membership is the sensitive information. Think about it. If you can prove someone's record was in a dataset for a cancer prediction model, you've just revealed their medical condition. If their data was used to train a fraud detection model, you've just implied they were under investigation. This has massive regulatory consequences under laws like GDPR, and it's so serious it's officially classified as a threat by MITRE Atlas. And just to hammer home that regulatory risk, here's another number for you. $2.8 million. That was a HIPAA fine directly linked to a membership attack on a healthcare model. The consequences are real, and they are extremely costly. Okay, so we know what it is, and we know why it's a huge deal, but how does an attack like this actually work? How do attackers find and exploit this so-called confidence gap between data the model's seen and data it hasn't? One of the cleverest and, frankly, most dangerous methods is what's called the shadow model approach. Now, here's the kicker. Attackers don't even need access to your private data to do this. Instead, they train their own models on similar, often public data just to learn what that behavioral fingerprint of membership looks like. Then, they come to your model, start asking it questions, and use the patterns they learn to make a terrifyingly accurate guess. And you have to understand, attackers are only getting better at this. The really simple attacks might see a 60 to 70% success rate. But the more advanced techniques, the ones using other neural networks to attack yours, they can hit success rates of up to 95% against a model that isn't defended. The threat is not static. It is evolving and getting much, much more effective. Okay, so this all brings us to the big question, the one you're probably asking yourself right now. Is my model vulnerable? Let's walk through the key signs that you might have a high-risk model on your hands. The number one vulnerability, the absolute root cause of this whole problem, is a concept called overfitting. This is when your model stops learning general patterns and instead just starts memorizing the training data. It's like it's cramming for a test instead of actually learning the subject. And that memorization creates that huge telltale confidence gap. That gap is the vulnerability.
And here it is. If you take one number back to your team, make it this one. Look at the gap between your model's accuracy on its training data and its accuracy on new, unseen testing data. If that gap is bigger than 10%, that is your flashing red light. That is a clear, quantifiable indicator of overfitting, and it means you have an elevated risk of a membership inference attack, period.
Now, other things can crank up the risk too. Small datasets, for example, mean each individual data point has way more influence on the model. Giant models, the ones with billions of parameters, have so much capacity they can't help but memorize things. And running the data through the model over and over during training, what data scientists call epochs, is just reinforcing that memorization. Oh, and if you see your model's confidence scores are all bunched up near 100%, that's another major red flag. Okay, enough with the problem. Let's talk about the solution. And I'll tell you right now, there isn't a single silver bullet. The real answer is a smart, layered defense strategy, combining a few different techniques to build up robust protection. So your first line of defense is all about fighting that root cause, overfitting. Things like regularization and dropout are just fundamental ML hygiene, really. But I want you to pay special attention to that last one, label smoothing. This is a brilliant little technique that basically teaches your model to be a bit less certain about its predictions. Just by doing that, by softening its confidence, you can reduce an attack success by a staggering 40 to 60%.
Now, for your most critical, highest risk applications, we have to talk about the gold standard. It's called differential privacy. And what makes it the gold standard is that it's the only technique that gives you a formal mathematical guarantee that your model's output won't accidentally reveal whether any single person was in the training data.
But, and this is a big but, this guarantee comes at a price. It's a trade-off, and this is a key strategic decision you'll need to make. On one hand, differential privacy can absolutely crush attack success rates. We're talking a 70 to 90% reduction. That's huge. The flip side, though, is that it usually comes with a 5 to 15% drop in your model's accuracy. You have to decide if that trade-off makes sense for your specific business case. A few other layers are also really important. You can use techniques to calibrate your model's confidence, or even add a tiny bit of random noise to its predictions to throw off attackers. And this last one is critical for compliance: machine unlearning. This is the ability to go into a fully trained model and surgically remove one person's influence, which is essential for things like GDPR's right to be forgotten. So the bottom line here is this: you just can't afford to deploy a model and just hope for the best. You need a practical, repeatable framework to test for and assess this risk before that model ever sees the light of day. And the good news is you can start today. There are fantastic open source tools out there right now, things like LiRA and ML Privacy Meter, that let your teams essentially attack your own models in a safe environment to actually put a number on your privacy leakage. So, what do you do once you get those test results back? Well, this chart gives you a really clear playbook. If your tests show that membership can be inferred with, say, 60 to 70% accuracy, it's time to add more defenses. If you're seeing numbers over 70%, you really need to stop and retrain that model with privacy enhancements before you even think about deploying it. It gives you a clear, data-driven way forward. So what can you do, right now, today? Here's your quick win for this week. Ask your team to take your highest risk model, the one trained on the most sensitive data, and test it using one of these tools. If that membership accuracy number comes back over 60%, a simple, immediate first step is to implement output limiting on its API. It's a quick fix that can make a real difference. And that really just leaves one final question to take back to your organization, to your teams. When it comes to your AI models, is their privacy just an assumption you're making, or is it a verified fact?